Some days I wish I could go back to the late 70s in programming, where you still had tiny teams building the programs and the programming language and the operating system and the hardware it all ran on as a single project. Also, some days I wish I could go back to the late 70s and just join a prog rock band. And this week we sort of get to do both. I'm joined by Dimitris Kyriakoudis, and he is co-building Raspberry Pi hardware that connects to synthesizers but runs a Lisp environment. So you drive the instruments and play music by writing Lisp code. It's a project that combines software and hardware and some long-term research theories about human-computer interaction, with the terrifying immediacy of live coding in front of an audience that wants something to dance to. It's just a wonderfully huge but self-contained project, and a truly full-stack project. And on top of that, it's an exploration of the things we still have to learn about the way we write software. Before we begin on this one, full disclosure, after we set a date to record the episode, Dimitri offered to send me the parts to build the hardware we're going to talk about. And I happily accepted. I spent about an hour soldering it all together, and I've been having some great fun with it, coding up some electronic music and making noises to slightly annoy my wife. Great. And I like to think I am journalistically incorruptible, but if you did want to corrupt me, sending me musical instrument hardware would be a great start. So I'll just say up front, having this definitely helped shape the parts of the project I wanted to ask about. But beyond that, Dimitri had no influence on the content, no warning of the questions that were coming. As always, I'm just here picking the brains of another brilliant software creator. So let's get started. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Dimitris Kyriakoudis. Dimitris Kyriakoudis, how are you doing?
Very well. How are you?
I'm very well. You're on one of my favorite topics, which is the interface between computers and music.
Oh, absolutely. That's my favorite topic too. So I think this is going to be fun.
Yeah, we're going to have a good discussion. So you are, let me say it in summary and you can unpack it with me, right? You are building specialized computer hardware for live coding of music.
Yes, and I would also add specialized software on top of that.
Specialized software too, yes. So unpack the music side of it first, because that's the least familiar to the audience.
Yeah.
What kind of music? Where? How?
So the kind of music is kind of up to the user, is up to the musician who uses these technologies. The technologies in question are live coding, which is a predominantly computational practice, and an analog modular synthesis, which is in a lot of ways also fundamentally a computational practice, but people don't really think of it as such. But a modular synth, let's start from what a synthesizer is. A synthesizer is either a digital program or an analog circuit that produces sound. Synthesizer, the word itself comes from the Greek word synthesis, which means to put two things together and kind of to compose. It's the Greek analog to the Latin compose. And so a synthesizer is a device that creates sound. Traditionally, they've been used since the 60s or 70s, depending on how far back you consider scientific equipment to have been synthesizers. But they've been used in all sorts of genres of music, and they've been interfaced with in all sorts of different ways. So there's the traditional piano-style keyboard that a lot of people use to play with synthesizers. Modular synthesizers have mostly controls in the form of encoders and buttons and dials and faders. But all sorts of different controllers can be used to control the parameters of a synthesizer. So the reason we're bringing live coding into this, and perhaps it'd be good to unpack the term live coding itself, because that's another very loaded term and very loaded practice.
Sure.
Live coding simply refers to to interacting with a computer program with its source code, with its actual implementation, as the program is running. So it's the dynamic interaction with the source code that generates a process as that process is unfolding in real time. And so it's been used by creatives to make music, to make real-time visuals, but it doesn't need to be a creative practice. I mean, people have live-coded physics simulations or other kind of algorithms just to get as short a feedback loop as possible.
Right. So you are. I'm thinking of a musician that sits down to a piano and thinks, okay, I'm going to play a 12-bar blues on the keyboard with some live improvisation. Mm-hmm. And what you're doing is the analog. I'm going to write a program that does the 12-bar blues that will drive the sound engine without a keyboard.
Yeah, that is more or less correct. The idea is that you're interacting with a so-called generative process. So instead of the direct manipulation of notes on a keyboard or strings on a guitar or even push buttons and dials on a modular synth, you are directly manipulating the code and then therefore indirectly manipulating the code's output. But we're interacting with a live computational generative process. And so, but this is not all too foreign to many electronic musicians, though. A lot of what electronic music production is nowadays is in a lot of ways generative and algorithmic. Whether you use a digital audio workstation program, or whether you're using a synthesizer with an arpeggiator or a sequencer, these are just fancy ways of describing algorithms that make certain parameters move over time. And those parameters can be the notes, they can be the type of sound that the notes are played with, or any kind of anywhere in the whole stack of the synthesis process. But live coding is fundamentally about exposing that kind of computational nature of these algorithms and not hiding them away behind interfaces that are fixed.
Right. Yeah. So when someone twiddles a knob on the keyboard on stage, you'd be writing a program that does the digital equivalent of twiddling a knob.
Exactly. Yeah. Twiddling a knob is nothing more than changing the value of a particular parameter. We can think of each module in a modular synthesizer as a function of sorts, and it has an API, and we can directly manipulate their arguments, or we can use other modules that generate abstract control signals, which are essentially just numbers that go up and down. And use those to control the parameter. But then we create this kind of almost recursive stack of algorithms that control algorithms that control algorithms that control algorithms. And so the whole thing is inherently very computational. Live coding just exposes that and says, don't be afraid of the code. The code is just the representation of what the process is doing.
So there's also a sense in which you're, as well as turning code into music, that you're turning music back into code for that to be the interface we play with.
Music into code. There's music is almost, whenever we're talking about a computational and algorithmic music process, and it's important to note that you don't need to be working with a computer to be doing algorithmic composition. I mean, Johann Sebastian Bach and others have done quite heavily algorithmic compositions on clavichords and pianos in the past.
Yeah, that's true.
So music in a lot of ways has always had a relationship with algorithmic thinking in a lot of cultures. And so what live coding tries to do is to make that explicit and maybe assign a clear and formalized vocabulary to all of that.
Okay, we have to get into the hardware of how this happens in reality. But since we're on the topic of code, how do you describe music in code? What have been your design choices?
So there's a lot of different paradigms and ways of thinking about the kind of computational nature of music. There's and in a lot of ways they're informed by the various different approaches and schools of thought and paradigms of programming itself. So there's almost a one-to-one mapping between object-oriented programming and some ways of algorithmically formalizing music, functional programming as well. The design choices that we've made are very closely aligned with functional programming, and in particular with purely functional programming, which maps to music in a very interesting way when you start considering music to be a function of its domain, which is time. And so part of how we designed the language that we're using had to do with taking that, almost pushing that to as an extremely literal level as possible. Can we write algorithmic music by literally writing it as a function of time? It's a function of one argument, one parameter, which is time itself in seconds. And as you keep evaluating that function with that argument increasing over time, starting from 0 and going on to infinity until we stop it, then the behavior of the music and the instrument is the concatenation of the output values of that function for every point in time.
So I would assume that everyone can imagine music as like a program that takes time as an argument and is a switch statement and says if it's less than 10, we're doing the intro. If it's 10 to 20, verse, chorus, outro. How on earth do you break that down into the individual adjustments of notes on a musical instrument and the individual parameters you're twiddling?
Yeah, that's a great question. The short answer is it depends on how you want to structure time. At the end of the day, time is just the linear flow, and it's up to us how we group that and how we twist that and how we make it either be a repetitive process or a completely chaotic one or anything in between. So in terms of notes, if you think of let's take the piano, for example, as an instrument. We have 88 keys, and each key has a fixed frequency to it. Each key has a hammer that strikes just a specific string or sets of strings, usually, that are tuned to a specific frequency. And so a piece of music played on the piano can also be thought of as 88 parallel streams of time-varying signals. And each one has its own fixed frequency, and what varies is just the amplitude at which that frequency is audible. And so what happens when we press a key on the piano is we introduce the little spike in the amplitude of that particular frequency at that particular moment in time, and then the string's natural decay kind of brings that back down to 0. And so in a lot of ways, that's just a graph that we can describe with maths and have those spikes be kind of generated as the time argument flows forwards.
Yeah, but that, I'm sure that works in theory, but in practice it absolutely doesn't work. If you've got 88 people with one finger, never mind getting the room for them, they couldn't possibly coordinate it.
Oh, absolutely not.
And what a pianist actually tends to do is coordinate groups of 5 things, right? Left hand, right hand.
That's exactly correct. Yeah, and that's where live coding comes in. It's you become the pianist who coordinates these things. You don't. Of course, you don't write 88 functions
right.
and go between them frantically changing parameters to play for release or something like that.
Yeah.
But the idea is that you start building this kind of tower of abstractions, each that pushes you towards a slightly higher level of how you want to be thinking about what's going on. You don't want to be thinking about 88 keys. You want to be thinking about a chord or a melody or a key modulation. And so programmers being programmers, we can build these layers of functions on top of functions that take very high-level descriptions, such as play this chord for a bit, followed by that chord, and kind of compile it down, if you will, to very specific instructions for different parts of the sound-making process.
Right. Yeah. So that starts to give me an idea of how you build up sound. So I'm going to write a function that takes the time and a root note and plays root, third, fifth, third over and over again.
Mm-hmm. Yeah, exactly.
And as I change either the time parameter or the root note parameter, I will get some kind of baseline which I then package up, leave that running while I focus on something else on top.
Exactly. So there's live coding tries to condense the feedback iteration cycle as much as possible, but there's still an element of I need to take a few seconds to think about what I want, the music to be doing initially. And then once you've built that up in code and you evaluate that, so there's an interacting kind of REPL-like evaluation loop. When you evaluate that and you send that over to your system and it starts producing music, then you're free to start thinking about how to proceed from there. And depending on the complexity and the kind of elaborate design of the code that you wrote, you may end up with code that does something that repeats every few seconds, and therefore you start feeling the pressure of like, okay, this has been repeating for a while now, I need to change it. Or you can also very, very just as well write code that does something over minutes or hours. And so you can have a live coding piece where it's a page of code and you press play and it does everything. Or you can have a line of code that you keep for a while, and then when you want a certain change to occur, you make that change yourself and reevaluate it.
Okay, so you would be expecting, whilst you could pre-bake the program, write the whole program, get it how you like it and play it, you're sort of expecting to have a live coding session where things are written, run for a bit, and then you throw them away to make room for the next thing.
Yeah, exactly. So there's almost a spectrum of how much of the performances or the pieces, if we're talking about a studio production piece, there's a spectrum of how much of its overtime behavior is currently encoded in the code versus how much of it manifests as and when I make changes to that code. And a particular piece of music or a particular performance can exist anywhere on that spectrum. We can have any combination of I've written the whole thing down and I just need to press play, and all of the overtime behavior is encoded in the code that's already there. Or we can have the complete opposite end of the spectrum, which is every single change needs to be made manually. Of course, that's very impractical. And so people don't usually reach that far into that end of the spectrum. But
you can go all the way from classical to free jazz.
Yeah, absolutely. And then anywhere in between. And we can play with rigid timing systems, free-form timing systems, or just pure chaos. I mean, computers are great at, we can just add randomness to anything and everything.
Yeah, no matter how it sounds.
Yeah. Well, we can. The question is, do we want to?
Okay, so you have chosen, let's dig into some technical choices here.
Yeah.
You've chosen Lisp as the interface language.
Yeah, so that comes out of a love affair is the only way I can describe it. With the Lisp family of languages that has been unfolding over the last few years in my life, and there are some highly technical, I guess, reasons for that too. Part of the superficial reasons for that decision have to do with Lisp's syntax and how you can have operators like plus or minus or multiply having multiple arguments. So you mentioned in the beginning that it's almost as if you can have these switch statements that say, well, if t is between 0 and 10, we do the intro, and if it's between 10 and 50, we do something else. How I like to think of this is I have all of these parts in my program, and each part can in itself be describing a process that is potentially infinite. If we have a sine wave just infinitely repeats forever. But if I don't want that sine wave forever, what I can do is simply nullify it before the beginning and after the end of the section where I want it to be active. So essentially what that means in code is multiply with 0. And so I think of a composition as a huge summation of every single part of the composition that will get multiplied by 0 when I don't want it to be active. So that's basically the same thing as muting it on a synthesizer or a mixing board. So
you are taking advantage of this language where everything's an expression, right?
Exactly. Everything is an expression, and expressions, because we have this kind of prefix arithmetic syntax instead of, in C or Python, we have the kind of infix arithmetic operators. And because this is another, again, completely superficial element to it, but when you're live on stage and you're projecting your code for however many people you've managed to rope into the live coding event, and you're feeling the pressure. You're feeling the pressure of the music being too repetitive, or of the audience being eager to dance more, or whatever it might be. You don't want to have to worry about things like semicolons at the end of statements, or you don't have to want to worry about adding commas between arguments. And you certainly don't want to have to worry about taking an expression and wanting to wrap it into another function call, and then having to navigate to the far end to open a parenthesis and to the other end to close the parenthesis. And so Lisp makes that easy with slurping and barfing and
structural editing.
Exactly.
Yeah. So, but does it also play into the, because one of the other things that Lisp is famous for is having a REPL, right? This interactive development experience. And is that another reason why you've jumped on this for live coding?
Yeah, exactly. So this is where the hardware that we're running all of this on becomes relevant. The module itself is powered by an RP2040 microprocessor at the moment. We can
Raspberry Pi, right?
Raspberry Pi, yeah, correctly. Yeah. It's powered by a Raspberry Pi Pico or equivalent processor, which is, by the standards of the previous century, it's a supercomputer, but but it would be kind of tricky running an LLVM compiler on it, and or running some kind of the JVM or any other large kind of REPL like.
You want a small light language.
Exactly. So we wanted a small language, not only one that's light for the microprocessor to run, but one that is very lightweight in its implementation for people to be able to fit it all in their head. And so I like to joke that this is the only programming language that I've ever worked with that I can understand all of it. I can understand the whole kind of stack of how it works, because it's a few thousand lines of C++ in this case.
I was going to ask, so it's written in C++?
Yeah, so it's been forked over by a so-called hobby implementation of Lisp. Adam McDaniel's Wisp, I believe he calls it. And it's a simple tree working interpreter at the moment, although there's a lot of plans for a specialized VM that kind of bakes a little bit of the time traveling capacities of this language that I'm sure we'll get to very soon. And so the idea is that the language implementation itself needs to be hackable. It needed to be hackable by us because we're not, industrial compiler engineers, and at the end of the day, we want to make music with this. We don't want to spend all of our time hacking on compilers silently. And so there's this beautiful simplicity that Lisp has in its core design, which I felt was particularly suitable for this kind of project. And then there's one last particularly kind of relevant reason why we chose it, which is so-called metalinguistic abstraction. So the ability to be able to build layers of language on top of language, essentially macros.
So does that mean you've got macros in the surface language?
Yeah. So there's the idea is that there is a stack which currently is mostly empty, but there's a stack where users can start inserting and removing layers of macro transformations. Oh, okay. And so each one, you can kind of think of them as passes in a nano passes in a compiler, where each pass does one thing. It will do constant propagation, or it will optimize expressions that are multiplied by 0, and so you can just kind of replace the whole thing with 0. But the idea is that as different musicians have drastically different needs. So not just musical needs, but also user experience and interaction needs. Someone might, be very keen on typing away for the whole performance. Someone else might want to have some high-level structural editing features so that they can jump between the live coding and, and a different instrument, perhaps, while on stage. And so the idea was that let's create this unifying core. Lisp and S expressions, in a lot of ways, we can think of as just a lingua franca. They just group objects together, and so we have that at the core. And then different people with different use cases can build slightly different dialects, almost on top of those layers, and then potentially even dynamically add them and remove them during a performance.
Oh, crikey, that's interesting. When would that be used? When different musicians take over on the same hardware, perhaps?
That could be the case. It could also be used. I mean, you can make slightly different mini languages that you use at the same time on the same hardware, in the same code editor. But the idea is that if you like, in a lot of ways, we think about things like sequencing drums versus composing a bass line versus coming up with chord progressions. We think about them in slightly different ways, often very, very, very different ways. But why should we have to express them in the same kind of language with the exact same semantics and the exact same syntax? And so a simple example in the beginning was, why can I, and this is something that not even most Lisps can do. I believe maybe, I'm not even sure if Common Lisp could do that with reader macros, but my thinking was, why can I not have a macro that takes in an expression and then the expression can consist of characters and spaces and so on. But then a white space is significant. So a white space indicates a rest, for example.
Oh, yeah.
Because in most Lisps, the reader throws white space away, and then all we can work with is what remains, which is symbols and lists and so on. But the idea was that, can we leave that possibility open so that if someone wants to use white space or indentation to mean something musically relevant to them, why should we not allow them to do that?
Yeah, you can instantly see how X space, XX space would be a rhythm, right?
Exactly, yeah. And there are
languages... It's almost a rhythm the second you say it aloud.
Yeah, absolutely. And it's a visual rhythm as well. You see it spelled out visually in front of you, geometrically. And all of these are extremely important. I mean, they might be completely insignificant for someone writing, production code in their office. But if you have the real-time constraints and this almost endless thirst for feedback when you're performing live, you want your computer and your editor to be able to tell you or show you what's going on as it's going on. And this is, again, where the kind of time traveling tricks come in, not just as it's going on, but potentially, if possible, before it comes on, before something occurs. You might want a bit of a heads up from your instrument.
Okay, explain. This is the second time you've mentioned time traveling. Tell me what you're talking about.
Yeah, absolutely. So this is a little bit, I guess, tongue in cheek. There's time traveling is, as far as we know, is not possible yet. But what we mean here is because we're focused so much on this purely functional paradigm, because we're literally treating time varying behaviors as very literal functions of time. The only thing that we really need to do to be able to preview what's coming is to just evaluate that function for a value of t that is the current value of t plus some offset.
So you've got a program, you could tell me what the note is going to be 3 seconds from now, because it's still just the same code.
Exactly. It's the same code. The code itself is I like the term inert or static for this. I've heard it used in the context of languages like Clojure or, code as inert data. So that the data itself doesn't change. The code itself can be statically analyzed, and so much about its over time behavior can be inferred just by looking at it. I'll give you a simple example. If we have a function like square just takes in a phasor, a value that rises from 0 to 1, and produces a square wave. A square wave is just a low and then jumps to a high, and it has a periodic behavior where it just jumps from low to high with a period of one. And most things in our language, which by the way is called modulisp, which is
modulisp.
It's a little bit of a play on words with modular synthesis and Lisp. Right. Also with the word modulation, which is a lot of what the module itself, which is called
µseq. That's the
µseq.
technical term for twiddling the knob, right?
Yeah, absolutely. Yeah. So we prefer to think of it as a modulation generator rather than a knob twiddler. But essentially that's precisely what it is. Yeah.
Right. Yeah.
And so because a lot of this overtime behavior is just statically encoded into the program itself, we can then do all sorts of neat tricks like, go into the future and see what's going to be happening in the next 5 seconds. And depending on what is coming in those 5 seconds, we might want to be able to change some things in the code. Or even more interestingly, we can statically... So you asked earlier, can you tell me what note is going to be playing in 3 seconds? And then there's another question that we can also ask the computer, which is, can you tell me when the next C note is going to play, or when the next D note is going to play, or when this sample is going to trigger next? So we can ask for it to kind of solve for T, so to speak,
right.
for various behaviors.
Would you just do that by running through the values of T?
No. So that's the obvious way to do that, and it can certainly work, but it's not very computationally efficient, especially when you're running on a microcontroller, and especially when that microcontroller's kind of runtime integrity is crucial for your performance's runtime integrity. So
you really don't want something to crash in the middle of a gig.
Yeah, you do not, and I've had that happen to me before. It's very. It's very nicely immortalized forever on YouTube, it's a lot of fun, reflecting back on it now, because it was at a functional programming conference, and so people are programmers are very familiar with crashes, and it was almost like a little mini game of like, can I fix the crash and bring the sound back before I lose the audience? Which live debugging under pressure. But instead of running through all of those moment by moment in time to get to whatever you're looking for, we can also just kind of statically solve for it. And this is not something that's currently implemented, but it's something that I'm working on as a part of my PhD on live coding instruments at the University of Sussex.
Okay, so you're actually doing a PhD on this. This isn't just like your new hardware business. This is also
this is so maybe it'd be nice to set some context for the actual venture behind which from which the module that we're talking about has spawned. So Immute Lab Instruments is the name of the company, and it's a company that we're launching with one of my PhD supervisors at the University of Sussex, Chris Kiefer, and Steve Simmons, another PhD student at Sussex. And the whole point is to bring research work that Immute Lab research lab at the University of Sussex. Immute stands for Experimental Music Technologies. And so the Immute Lab has been working on all sorts of sort of research projects around musical instruments and musical technologies and interfaces and so on. And so the idea was to start bringing those from the research domain to the commercial world and start making them publicly available and accessible for people, because there's this problem in the academia that people, will come up with a new instrument idea and they'll make a prototype and they'll write a paper about it and present it once or twice, and then it kind of sits at a shelf and no one ever really gets to play with it. And that's one of the worst things that you can do to a musical instrument, is not put it in the hands of people who want to make music with it.
Yeah, because unlike software, once you've got hardware, you have to commercialize the production of it or no one gets one.
Exactly. Yeah. And there's, modular synthesis and Eurorack, which is the particular, I guess you can call it a platform. It's a set of electrical and mechanical standards for how to produce modules that work together. So they use the same power supply, they fit in the same racks, and they more often than not, but not necessarily always, speak in the same voltage ranges. And so they can kind of talk to each other. But the problem with that is that can get really expensive really quickly. If you're buying all of these individual components and they're all made by, in small batches, potentially by boutique manufacturers, you very quickly get into the thousands, if not more, if you want to build a kind of functional system. And what we wanted to do is to try and kind of flip that on its head and say, well, how can we cut cost almost to the bare minimum. And so the first incarnation of this module was a DIY prototype with an actual Raspberry Pi Pico, not just the chip on a PCB, but the actual Raspberry Pi Pico attached onto a 3D printed board with hand soldered wires between everything. And the idea was to make this a super accessible DIY project for anyone to build in an afternoon or a weekend, depending on your level of kind of familiarity with DIY projects like that.
If you're handy with a soldering iron, it will
exactly,
be quicker.
And it doesn't really take much more than that. And if you have access to a 3D printer or some other means of creating a panel, all of the schematics and the hardware design files and all of the source code, by the way, is completely open source under a permissible license. So we wanted this to become something that a community can be built around. And something that would not be prohibitive due to cost. So people could buy the bare materials for around 20 or 30 pounds, depending on where they live in the world. And then DIY this, flash it with the firmware, make alternate firmwares, make alternate editors, whatever it is. We wanted to make this an open source product and also an open source company in general. So most, if not all, of the things that we're working on at the moment are open source.
Including the hardware?
Including the hardware, yes. So the PCB design files and the CAD files for the face plates and everything else, yeah.
Okay, so teach me the big missing piece that I don't know. I can imagine having access to a synthesizer, like someone like me. Actually, in reality, I have access to many synthesizers, and it's become a problem. but I can imagine. I'm
familiar with that problem.
Yeah. I can imagine having access to a synthesizer. I want to control it with some external live coding controller. I know how to write a programming language or port one. I probably can figure out how to get it to compile to Raspberry Pi. And then I think my knowledge caps out. How do you go from this is running on a Raspberry Pi to this is actually sending the right voltage signals out of it to something else? What's the hardware part of this puzzle?
Right, yeah. I might not be the best person to ask for this because I mostly work on the software side of the module.
So the answer is get someone else.
The answer is, the short answer is ask Chris Kiefer on our Discord or if you happen to run into him somewhere. But the answer is, the Raspberry Pi has analog outputs. And it has, and by analog outputs, we mean you can call a function with a value. I think it's 12-bit, but I might be mistaken. You can call that, and then one of the pins on the board itself will send out a voltage.
Right. There isn't just 1 or 0 that's variable between. You can output floating point numbers as voltage.
Yeah, so the trick to get floating point numbers as voltage is to use so-called PWM, which stands for pulse width modulation.
Tell me about that.
Well, let's talk about what a pulse is. An electrical pulse is just a signal that goes from low to high. So you think of just a binary kind of analog gate that can either output a high voltage or a low voltage. The pulse width is the duration in time for which that pulse is high versus low. And so by modulating how long that pulse, that binary pulse, stays on high versus on low, and then by putting that whole thing through a filter, a filter in the mathematical and electronic sense, you essentially smooth out those jagged kind of binary on and off transitions. You smooth them into a wave that actually kind of continuously interpolates between these values.
So am I right in thinking if I want to output a value of 0.75, so I just flick my switch on for 3/4 of the time and off for the other quarter of the time, and that jagged output can get smoothed out to the average of 75%.
I'm not exactly sure that it would be the kind of 3/4 and 1/4 ratio.
Okay, so the maths may change, but the idea that you flip
exactly.
it back and forth in the right proportion.
This becomes a little easier to intuitively picture if we think of filters as something that makes a signal lag a little. So we have a signal that's very jittery, let's say very noisy. And we can imagine it as a very chaotic, noisy signal. If we put that through a filter, what the filter does is it tries mathematically. What it does is it attenuates the higher frequencies above a certain point, which we usually call the cutoff frequency. And what that means in practice is that we take a signal that's very jagged, and you can almost think of it as attaching some weight onto the object that's creating the signal. And because we make it heavier, we make it have more inertia. And because it has more inertia, it resists kind of very quick, snappy changes to its position. So it almost becomes heavier and then it starts moving in these kind of smoother patterns. Not unlike how objects that, if you have two balls and one of them is extremely heavy, like a bowling ball, and then we have a similarly sized ball that's empty inside, it's just filled with air. The lighter ball we could slap around very quickly and easily, but the heavier ball would resist these almost instantaneous changes to its position a lot more.
Okay. So now I'm thinking, if I want to get my 0.75, what I'm kind of doing is watching this voltage slowly fall down to 0.74. I flick the switch on, it starts slowly rising above. I flick it off, it starts slow, and eventually it smooths out to the actual value I want.
Yeah, I'm no electronics engineer by any stretch, but that's how I think of it. Yeah, right. That's how I understand it.
And then my job presumably is to arrange the right size of resistors and capacitors to make this. I have to go away and research filter circuits in resistors and capacitor values.
Yeah, more or less. I think it's one. This is an already established practice. A lot of devices work that way. I think I might be mistaken on this, so please nobody quote me. But I think a lot of synthesizers used to work that way with PWM outputs that would generate sound that way. But that makes it a lot cheaper, and it makes it a lot easier. And the coding for all of this is already abstracted away on in libraries for Arduino or Raspberry Pi or similar. And then the filter circuits themselves are you can just pull one off the shelf, so to speak. So we didn't reinvent any wheels. We didn't need to design any kind of groundbreaking system to do this. What I believe to be the novelty of the kind of the whole design is the idea of putting the interpreter in the module instead of having to re-flash it every time you want to make a change to the code. So there's already quite a few modules out there that are programmable, but by programmable we mean we have to write the code, compile it, flash it, use it for a bit, then think of what changes you want to make and repeat that cycle.
Yes, because the big thing here is that the programming language interpreter isn't running on my laptop; it's running on your Raspberry Pi module.
Exactly. Yeah.
So I can, I can constantly send new code. Okay, I start to see how I would Let me ask you one more question about building the hardware before we move on. Once you've figured out that circuit board and you've done some prototypes locally with, like you were saying, wires and soldering it yourself, do you just sort of, I don't know, do you just go to a factory in China and say, can you make 1,000 of these? Here's the circuit diagram.
Yeah, so that's definitely an option. Our initial option was, so we got the PCBs printed. PCB stands for printed circuit board, and it's just a board with the, instead of wires that go from one point to another, there's a trace of some conductive material on an otherwise not conductive board. That essentially are a compiled and optimized version of what the wires were doing.
Right.
And so we get the PCBs printed. PCBs are quite cheap, and especially if you print them in high volumes, they can cost as little as a couple pounds, or a lot less if you go into the thousands in terms of batch sizes. But we got the PCBs printed, and then we booked out 3 days between the three of us, and we sat down around a kitchen table, and we made those ourselves. So we ordered all of the components. We ordered the PCBs. A lot of the PCBs nowadays you can order with the surface mount components already installed. So the factories have, I think they're called pick and place machines, the little robotic arms that will pick these tiny little electronic components and place them exactly where they need to be on the PCB, and then solder the whole thing in one go. And it's extremely efficient. And so we get the components such as the aluminium cut faceplate, which again, you just send the design file to a manufacturer, and they will cut it and print on it, all the labels, everything. Then we get the jacks for the cables, the encoders, every other component that's required. And then we put it all together ourselves, and neatly packed it in a box and send it off to the distributor. But the idea is that now, if we want to be able to make this if we want to make the production of this module more sustainable for us, which it's not really sustainable to take 3 days or 4 or however many is required out of our busy professional and academic lives to build these every time. We've gotten in touch with various manufacturers, some of them actually quite large, and they do a lot of medical equipment, or they work on any kind of sort of what they call electromechanical assembly, which is basically taking the boards and all the components and soldering what needs to be soldered, snapping in what needs to be snapped, and tightening the screws and putting it all together. But then more interestingly, a lot of smaller manufacturers that specialize in lower production, lower size batches, specifically for electronic music equipment, and in our case, specifically for Eurorack modules. And I believe, I believe that one is based in the UK.
Okay, that sounds interesting. I would have guessed nearly all of this is happening in Eastern Europe or China, but
a lot of it, if not most, is Okay. There's a lot of companies that also hire out their own assembly line for things like that. So there's some companies based up, I believe, in Poland, if I'm not mistaken, who have their own production facilities for their own products, but then you can also hire them to build yours.
Okay, so the path to productionalizing, if that's a word, your software ideas as hardware, it's fairly smooth, you're making it sound like. You don't need to build your own factory.
That has been our experience, yeah. Cool. There's a huge market of companies where you just send them your files. And again, all of these files are available on the GitHub, so theoretically anyone could download them and send them off to a manufacturer and order a batch of, 100 or 1,000. But yeah, it's actually quite smooth. And in terms of prototyping purposes, you can order smaller batches of 5 or 10.
Okay.
And the turnaround times are not terrible. We're talking in the weeks, not months.
It's actually impressive for turning an idea into actual hardware. Oh, yeah. Cool. Okay, so let's pull it back to once you've got your module. What's your real aim with this? Are you Are you trying to get a PhD? Are you trying to become a synthesizer manufacturer? Are you trying to gig with your ideal synthesizer setup? What's in it for you?
The shortest answer is yes.
I had a suspicion it'd be a balance of all three.
Yeah, it is all of the above. So the module itself is part of my PhD, quite a core part, I believe. The PhD itself focuses on what I like to call the triple E triangle. So the ergonomics, ergodynamics, and ergologics of live coding instruments and practices.
Right, unpack that for me, because I think I know what ergonomics is.
Yeah. So as you know, as programmers, we love defining things. So I'll define some terms first.
Great.
Ergonomics comes from the concatenation of the two Greek words ergo, which means work, and nemo, which means or nomos, depending on how you think of it. Nomos means law. So if you go that route, you can think of ergonomics as the law for how things work. The rules, almost, so to speak.
Okay.
If you go the route of nemo, which is what I prefer, nemo means to distribute or to hand out or to give. And so then ergonomics becomes, in some ways, the distribution of labor. That's how I like to think of it. So something is ergonomic when it distributes the labor that's required to work with it appropriately. So when I'm using my mouse, for example, and I'm constantly making these left and right movements with my wrist, that's not particularly ergonomic because I'm overworking a very small group of muscles that's not necessarily designed to withstand this kind of abuse over years and years and years, which is where things like repetitive strain injuries and so on come along. And my personal interest in all this is that I developed lateral epicondylitis, also known as tennis elbow, at the ripe age of, I think it was 16 or 17, I don't remember. And it's more or less been with me ever since. And it's now something that I've learned to work with and work around and change the way that I interact with, my computer and my keyboard and my mouse and all of these things. So as to avoid making it worse. But that led me down this massive rabbit hole of why does almost every single mouse look that way? And why do almost all keyboards look like typewriters from the late 1800s? Mm-hmm. And this rabbit hole eventually leads to, I guess it's for financial reasons, because there's, typewriters became fundamental to running a business at some point in history. And then new technologies came along, digital computers and so on, but businesses could not afford to have to retrain all of their employees to now type on different keyboards. They had to be able to buy the computers and jump onto this new technology from day one and be productive. And we've kind of been stuck with these designs that have not been designed with ergonomics in mind. In fact, the famous legend is that the QWERTY keyboard's layout came about because the typewriters with their little mechanical heads that would punch the letter, if you were pressing adjacent keys very quickly, there was a chance that they could block one another.
It would jam together.
Yeah, the whole thing would jam and would not work very well. And so in some ways, the design of the QWERTY keyboard had the goal of spreading key presses around the keyboard as much as possible, randomly in some ways. Whereas what we really want is to minimize the amount of work that our fingers have to do, which not only makes us type faster, but it also reduces the chance that we'll develop and worsen things like repetitive strain injuries.
Okay.
So this is the ergonomic part. Ergodynamics now is, again, ergos, which means work, and dynamis, which in Greek means either power or potential. And so ergodynamic, you can think of it as the feeling that you get when you approach an instrument or any other system, really, the vibes, almost, so to speak, that you get from it in terms of what its strengths are and what its potential is in order of in the sense of producing work. So in the case of an instrument, we'll take the piano as an example. You sit in front of a piano for the first time, and you don't have to be a pianist to realize that, okay, I have all of these keys, and what this instrument can do is play any number of them at the same time. I could, like, in theory, just, lie down on it and play all of the notes at once. But you don't see any knobs or dials or buttons or anything to really substantially change the sound. And so you get a certain feel from the instrument about what it's guiding you towards doing with it. And of course, there's always, you can always go the experimental route and take the covers off and start sticking things between the strings and playing it in ways that it was not intended. But that still is part of its ergodynamics. So how does its design delineate almost what its potential for sound production and musical performance is?
Yeah. Like a cello. I'm thinking of a cello. That's something where it's kind of hard to make a specific note, but very easy to vary the tone of it from day one.
Yeah. So very different instruments give us very different feelings and feels about in terms of how they work, and they all guide us, whether we realize it or not. They guide us in various different ways to make different music. So, for example, I also play electric guitars, and I love thinking about all the tiny little, differences that, you have a single coil pickup or a double coil humbucking pickup. And that's a very technical distinction. It's like, how is the whole circuit wired, and how many, how long is the coil, and all of these things. But at the end of the day, they feel very different. There's music that would not have been created if the person who made it was holding a guitar that sounded significantly different, because then they would have, interacted with it, and the feedback iteration loop would have led them to a different musical outcome.
I'm thinking of a Telecaster, which is the classic country guitar.
Exactly.
And it just has that certain sound that feels country.
Exactly, yeah. And similarly with the Les Paul and the Stratocaster. And so ergodynamics in a lot of ways has to do with, what is the bidirectional relationship that you have with the instrument in terms of how you use it. Not so much in a practical sense, like ergonomics. Ergonomics is more about how does it sit against your body? How far do you need to twist and bend your limbs in awkward positions to work with it, and what does that do to your body after many years? There's a lot of professional musicians and performers have famously gotten very bad repetitive strain injuries after decades of practicing the violin or the piano for days and days on end. And then lastly, ergologics. This is a term that I haven't really seen used very widely, and I tried to Google for it, but it only came up in the context of, I think, a company in its name or something like that.
You have this advantage with your Greek heritage. You can just make these words up, and they're real.
Absolutely. It's a cheat code. And I'm very, I always say that if I hadn't been raised with Greek as my mother tongue, I would have probably never bothered to learn it, because it's not a very useful language outside of Greece. But precisely in these ways of lexical synthesis, both of which are Greek words, by the way, you can very easily kind of stick two and two together and get a new language, a new word. Sorry. So the word ergologic, I kind of think of as ergo, again, work. All three of these words share the same first half. And logos in Greek means either speech. In modern Greek, it's come to mean when you give a speech. It also means speech as in the actual act of speaking. And it also alludes to the notion of logic and reason. So the logos of you doing something is the reasoning behind it. Why are you doing this? And so ergologic is, I like to think of it as, how do we as potentially technical people who are, intimately familiar with the actual engineering details of how some of these systems work, how do we reason about what's going on? How do we reason about why the system has been put together this way? Or if we put it together that way, why did we do that? And what's actually happening? Do we have a JIT compiler somewhere? Is it an interpreter? Is it a tree walking interpreter? Or does it work in some other way?
Is this like when I'm debugging, what I'm kind of doing is creating a mental model of how the programming language worked and evaluated this software?
Yeah, so you're modeling the ergologics of the system in your head. That's how I like to think of it. And the reason why this is relevant, and just to go back to the topic of the PhD, it's I am focusing on the interaction between these three variables. Therefore, the triple E triangle, right. Because it's almost impossible to change any one of them in a system without affecting the others. And so
bring us back to the concrete for me. Like, describe how these factors influence your design of your module.
Yeah, absolutely. So ergonomics was the kind of initial motivation. It was this idea that, well, I love computer music, but I also love real-time direct interactions with musical instruments. I grew up studying the piano. I play guitar, bass, and I love this feeling of tinkering with an instrument in real time with my hands, and this immediacy that it gives you. You get into these flow states, and you're not really thinking about what's happening, but you're reacting both at a physical embodied level, but also at a cognitive level, whether it's creativity or rational thought, or any mixture of the two. And so I had this problem where I was playing with software programs like µseq or Pure Data or other so-called virtual patching environments, modular patching environments. And the idea is that you have a blank canvas on your screen, and you use your mouse to pick and place modules or objects. You can think of an object as essentially just a function, and it has some inputs, and it has a one or more outputs, and you physically, you click and drag to connect these with virtual wires.
You're drawing a graph of what your processing graph looks like.
Yeah, pretty much. And it has a lot of pros. As for example, you just mentioned, it is almost a one-to-one direct visualization of a computational data flow graph. And so it's very intuitive to work with. The problem that I had with it was, one, it's a particularly mouse-heavy workflow, and the mouse, at least modern mice, non-ergonomic modern mice, have the issue of extended pronation, like extended periods of time of pronation of the arm. That means the palm of the hand and the wrist are parallel to the desk and to the floor, and so the hands are in a kind of generally uncomfortable position for long periods of time to be in, due to how the bones in our forearm, in the elbow, they're fixed, but the wrist obviously can rotate, and so they create a pinching of the tendons that run through the forearm. And then as you're using those tendons while they're pinched, while your arm is in this kind of pronation position, that severely wears them out over time, or at least it did in my case. And so that was the ergonomic issue there. It was this idea that, well, I love this, but the more I work with it, the more it hurts, and this is not sustainable. I can't keep working like this to make music. And then the other problem was a problem of ergonomics and ergodynamics, and that was that I didn't get the feel, working with these systems, working with µseq or Pure Data, I didn't get the feel that I could develop muscle memory that I could rely on over time.
Yeah, mice are terrible for muscle memory compared to keyboards.
Yeah,
right?
absolutely.
Yeah.
And the reason, part of the reason is because what you're doing with the mouse physically at any given moment depends on where it is on your desk. So if it's, if you've pushed it very far, you're going to need to lift it and move it, or work in that kind of position, which might be uncomfortable. But also it is entirely dependent on what's on your screen, where it is and where your mouse pointer is in relation to that. And so it actually becomes really hard, and I personally believe impossible, to build any kind of muscle memory that doesn't depend on you looking at the screen the whole time. And if things dynamically move around your screen, if you're jumping in and out of windows, if you're moving windows to the side so that you can see something behind it, all of these things throw you off in terms of muscle memory. And it might not seem like a big problem, but when this all ties down to you're on stage in front of an audience and you're feeling the pressure. You don't want to have to spend those extra 3 seconds or 2 or even half to, find where on the screen that button is, and then find where your pointer is, and then work out how to move your arm so that the pointer goes to the button.
Yeah, in high stress situations, it's all about what you can do without thinking. Yeah,
exactly. So it becomes very important to be able to develop this muscle memory over time in the comfort and privacy of your own house or studio while you're practicing your craft, and then knowing that you can rely on it. And this is not just important for high stress situations, but it's also important for what we call flow experiences. It is almost impossible to get into a state of trance, tweaking parameters on a screen with a mouse. And for me, I missed these kinds of, I'm not really thinking right now, I'm just doing, I'm reacting. And obviously there's thought that goes into that, but it's not thought that I consciously have to initiate and engage with at every stage and feel frustrated when it doesn't work and so on. And so the motivation for the PhD was, can we come up with not just different interfaces, because a keyboard already exists, MIDI controllers with knobs and faders that can be mapped to any arbitrary parameter exist. But the problem is we don't really have or at least I believe, we don't really have a good paradigm for thinking about kind of how we structure these systems. It's a bit of a free-for-all. Every environment just gives you this kind of blank page, and then it's up to you to figure out how to map physical engagements, how to map button presses and dial movements and fader pushes, how to map those or what to map those to. And is it then the whole other aspect of how does that happen in the digital? What are the ergonomics and what are the ergodynamics of the computational thing that we're actually interacting with? Because there's, physical ergonomics is one thing, but then programming languages have their own cognitive ergonomics. I mentioned earlier the having to remember the semicolons at the end, or having to worry about indentation in some languages, or these sorts of things.
So is it fair to say on this then that you have... I'm sort of paraphrasing here, but it's if I'm playing guitar, if I'm playing the piano, I can forget myself, forget the object I'm holding, and lose myself in music. And it sounds like on one level you're asking the question, could we create that with making music with a computer?
Yes, but more specifically, making music with a computational process. I always love going back to what Hal Abelson says in the first episode of the 1987 MIT course on structure and interpretation of computer programs. I'm sure some of your listeners will be familiar with that textbook.
Yeah, and I've got the book up on the shelf somewhere. No, I'm not going to look for it. It's just there, out of reach.
Exactly. It should be on every programmer's bookshelf, I believe. And cheers to Sam Aaron, who tweeted about this once randomly, and I was like, well, if Sam Aaron, who's made live coding instruments that I've enjoyed and been inspired by, endorses this book, then I'll check it out. And it became my bedtime kind of watching almost for a couple of weeks. And so what he says in the first lecture is computer science is a terrible name for this business, because it's really not exactly a science in the same sense that natural sciences are, but also most importantly, it's not about computers. it's almost in a way substrate independent. It's not about whether we're using digital computers or analog or quantum or whatever. It's about computation as a notion in general. It's about information and what we do with it and to it. And so it was, can we bring these embodied flow state trance-like experiences to the practice of working with computational processes in real time? How I like to think of it is, or how I like to summarize the research question in a very high-level, abstract, potentially not very specific way, is what would it take for a programming language and the interface to that programming language to be designed in such a way that I can study it and practice it at home and then go on stage and close my eyes and just improvise?
That's a beautiful image. So I have to ask you, I have to put it on the spot. So you've built this module as almost a hypothesis of what that would look like. And what do you think your results are?
Yeah, so it's the first kind of concrete testing of some of the hypotheses. So one of them was, we clearly went down the route of picking a very low-powered computer to put inside a module, to put inside a modular synthesizer case. And then there's the obvious question, well, why don't we use a laptop instead? I mean, we have these extremely powerful computers already. There's tons of software. We're not limited to however many megabytes of RAM microcontrollers have. Part of that, the answer to that question is we don't want to feel as if we're working on this, playing music and improvising on the same machines that we work on during the day. We all spend just amounts of time in front of a computer that some years ago we wouldn't really have imagined we'd be spending so much. And so the idea was, can we put the computer in the modular instead of having this distinction between here's the thing that makes sound and here's the thing that I interact with mostly to control the thing that makes sound? Why can we not just have it all be in one instrument that I can put in a suitcase and bring with me to a jam or to a gig and play with that? So rethinking a little bit what the personal computer looks like. And then the other thing was, the world of Eurorack modular synthesis is already filled with modules that are meant to be interactive controllers. There's joysticks, there's XY touchpads, there's all sorts of other modules that you're meant to touch and play with physically. And then the question was, well, can we use those in the codes a little bit? Maybe I don't want to have to type the exact frequency of my low-pass filter. Maybe I just want to have an XY pad that I can use to explore the space of parameter values.
So you're saying that this standard of Eurorack gives you a pre-built library of other pieces of hardware you can mix into what you're trying to achieve.
Exactly, yeah. So there's companies with large engineering teams that have designed three-dimensional joystick controllers and then there's other companies that have developed things like the Leap Motion or other controllers that kind of track movement in one way or another. There's all of these almost abstract blank slate, components that you can use in a system. Why don't we build something that can read those in? So our module has a couple inputs, and then there are more expander modules on coming along the way to kind of scale that up as high as we want it to go. And the idea was, can we just get some of those modules, or if we already have some, can we use those to directly change parameters in the code? I can set up a half a page or a page of code the way that I like it, and then leave these like well-placed holes in the code where I'm like, this is where the joystick goes, this is where the XY pad goes, this is where the pressure sensor in this module controls the code, and then how the kind of custom software comes in as well is, once I do that, can I have can I have whatever monitor I'm using, whether it's my laptop or my tablet that I'm using to send code to the module, or maybe a dedicated screen that's built into the URL case itself. Can I have that visualize in real time what my hardware physical controls are doing to the computational structure of the code? Can I move the joystick and see the number go up and down?
Okay.
And as it's going up and down, I can hear what the smooth motion of the joystick is doing, and I can see what the changes in the numbers are. And over time, hopefully that helps me build an intuition about which kinds of numbers get me which kinds of sounds, and how would I go about kind of bidirectionally traversing this in my imagination as I'm performing live.
Yeah, teaching your brain how it's all related by making sure different parts of your brain are actively being stimulated. Yeah. Okay, so that opens up something wider than music, doesn't it? Because it's like, for years we've done all our coding with keyboard and mouse, and if you can weave in this whole range of other different ways of interacting with software and with the ideas you're trying to code, what are the possibilities?
Exactly. And this all, it touches upon things like interactive and incremental development. There's a reason Lisps are being praised for having this incredible development experience, because you're trying out things and you can experiment with minute changes very quickly in ways that write, compile, execute, wait for the test condition to be reached, and kind of
Lisp has always felt more like a conversation with the computer.
Exactly, yeah. And that's exactly what you want to have with a musical instrument as well. You want a conversation, or at least I want a conversation. I don't want a musical instrument where I sit down and write a letter and post it, and it takes a few days to arrive, and then we have this kind of correspondence back and forth.
Yeah, keyboard is not a pen pal.
Yeah, exactly. And so there's people already working on things like that in the wider computational context. There's structural editors are great for then pairing with hardware controls. I have here a split ergonomic keyboard that has a built-in encoder in it, and so while I'm
got
coding,
one of those keyboards for the people that aren't on YouTube. You've got one of those keyboards that splits into a left and right hand, and it's also got value dials on it. Yeah,
exactly. So it's a so-called ergonomic ortholinear keyboard. Ortholinear meaning that the rows are not staggered between them. So it's just a straight line up and down for fingers to extend instead of having to go diagonally in all sorts of weird ways.
The layout fits your fingers rather than fitting the available space on the computer.
Exactly. Yeah. And it's designed with the pinky column is brought a bit further closer to the pinky, so you don't have to stretch, and it's ergonomic in a lot of different ways. But my personal, I obviously cared about the ergonomics of it, but I was fascinated by the idea of having an endless encoder built right next to my keys. So as I'm coding, I can navigate to a filter frequency parameter, and I like to say instead of live coding and playing my instrument with my prefrontal cortex by pressing backspace and deleting the number 4,600 hertz and writing 4,700 hertz instead to see what that sounds like, I can just navigate to that number and have my editor be aware that I'm actually I've navigated to a number now that can be manipulated. It's not just a string of digits that then a parser needs to get involved and all of that. And then can I just move that endless encoder and have that number go up and down and hear the effects in real time? And so instead of playing with my prefrontal cortex, I'm playing with my ears and hands instead.
Yeah. It's kind of offloading the writing of code to your hindbrain, right? Mm-hmm. So your forebrain can focus on what the task you actually want in hand is.
Exactly, and my brain can take a moment to listen to what's happening and take it all in and get a feel for what the music is doing and what the audience is doing and how it's reacting to it, and basically just be more present instead of being all up in my head thinking, have I got the order of arguments right? And is this the right syntax? Is this spelled with this L or this double L or things that are, I mean, ultimately they are important. We can't, misspell code and expect the computer to magically know what we want. But why are our editors so kind of blind to all of these, to all of these conditions? Why don't they help us, pick functions from a list of similarly spelled, or why don't they give us the option to turn a block of code, let's say a case switch statement? Why don't they help us instantly transform that into the equivalent, if else series of statements? Because these are all kind of, there's well formed methods from going from one to the other. But if in that moment I feel like it would be much more conducive to my flow for the code to have a slightly different form, I would like my editor to be able to be taught what those forms look like and how going from one to the other should happen.
Yeah. I do think that whilst we've made terrific progress in computer science since the 50s, we're still in the infancy of how we speak to them.
Yeah, absolutely.
Okay, so let me ask you, perhaps as a final question, let's take it out of the lab and put it into hard reality. I think I'm right in saying you've used this approach and your hardware and your software to play live. What was your actual experience? Did you come away delighted with what you built? Did you come away wanting to make fundamental changes?
Both in some ways. There's the feature list is never complete enough. The editor is never smart enough. I mean, there's a lot of these things that I've talked about are not necessarily things that have been implemented yet. There's a very long roadmap that involves doing some background research, reading on what people have been doing to tackle these problems since the 80s. I've got a couple of books behind me called Visual Programming Environment, Paradigms and Systems and Applications and Issues. And they date, I think, from the 70s, if I'm not mistaken, or 80s.
Oh, wow.
And they look very much it. But, it was kind of mind-blowing to see that people have been trying to tackle these problems for so long, and they've so many different testing systems were put together for these sorts of things, and we still haven't quite solved it. I mean, there's if such a great new paradigm had been developed already, I would like to think at least that people would have started migrating towards it. But so I've been frustrated when using these systems by the very things that we're now planning to move it towards anyway. So I've been frustrated by having to have my laptop next to the module. I mean, I can use the inputs to use other encoders and so on. And there's a couple of encoders and push buttons and switches and so on the module itself. So there's a little bit of tactility there already, but fundamentally, I'd still probably need a laptop and a keyboard, or at the very least, a tablet and a keyboard. We have a little setup that we demoed at Bristronica in Bristol a few months ago, where this was
a music expo for music technology.
It's a music synth sort of technology and instrument expo, and we didn't want to just have laptops and modular cases on our table, so we thought, well, what if we just put a Raspberry Pi inside the case and a little screen and a little keyboard attached to a mechanical arm that is that can be set on the case, and so kind of try and bring the whole thing closer to a coherent system rather than this almost disjointed combination of here's a laptop over there, here's a modular over here. So I've been definitely frustrated by all of these, but at the very same time I've been delighted by the fact that I can now bring together these two worlds. I've been playing with modular synths for a while, and I've been playing with live coding for a while, and they've always lived in different worlds. They were always islands that it was either impractical to connect or very expensive. You have to buy so-called DC coupled audio interfaces. So that means a converter that can take a digital signal, produce an analog signal, but not filter out frequencies that are lower than audible, right? That if you're plugging a computer to speakers, you really don't want to send a voltage that's like constantly at a high level, because the speakers need to move, they need to oscillate, and you can damage speakers by trying to just keep them pushed in one end of their oscillation or the other. So these are expensive, they're clunky, they don't scale very well. And now suddenly I could take the code that lives over here in this little island and send it over a very thin USB cable to the module, and then have the module run it, and suddenly it speaks the language of the whole other island. It generates voltages, it can read voltages, then those voltages can be sent back to the computer, they can be visualized. So it has been a validation of the fact that there's something here that needs to be refined, and something that can be evolved into a whole ecosystem where modules talk to each other, not in voltages anymore, but in code. There's this kind of desire that I have for modules to be able to tell each other more than just, here's the result, here's the output. They should also be able to communicate processes. They should also be able to say, hey, I'm a filter and these are my parameters, and I'm receiving an oscillator and it has those parameters, and maybe I can tell the oscillator to change some of its parameters before it sends me its signal, and have this kind of paradigm of things talking to each other at an actual semantic level.
Subcomponents of a musical instrument chatting with each other to try and achieve the job.
Yeah, I mean, you can think of it as a distributed computational system where instead of just running, instead of just having remote procedure calls that say, here are the arguments, you have the function, run it and give me the result, can we share code? Can we compare what we're doing? Can we have a symbolic, meta-linguistic, this is, again, where Lisp is extremely useful. Can we look at code and unpack it and potentially maybe change the code before we run it, instead of taking the output and running it through more code, and no bit of code knows about any other bit of code either before it or after it.
Nice. Yeah. Let me just ask you one last quick question then, because there's a definite overlap between what you're doing in hardware and what Sam Aaron, who you mentioned, is doing entirely in software.
Yeah, so so what Sam Aaron does is not just limited to software in my opinion, in the sense that he was one of the first few people that I saw performing. And this was not necessarily live. I think it was just he posted a photo of his live performance setup before a gig on his Twitter account at the time, and I was fascinated by the fact that it looked like a live performance setup. It didn't just look like, here's an off-the-shelf laptop on a desk with an off-the-shelf audio interface. He had an ergonomic split keyboard. He had a MIDI controller with LED lights on it to visualize things in the middle. He had a synthesizer that he was taking the sound and putting it into the computer, but also the computer was sending messages to the synthesizer. So there was this kind of like, this is all a system that is put together for me to perform tonight.
Yeah, so he's drawn into the hardware world too. Yeah,
exactly. And I don't know that whether he has made any custom hardware or is using whatever components are and parts are actually available. But this idea that Sonic Pi, his perhaps most popular and perhaps the world's most popular live coding software, which is used in the UK to teach the computer science curriculum in schools. And it was funded by the Raspberry Pi Foundation and all that. That was the first live coding program that I, first of all, installed without any issues. Because live coding systems are notorious for, you need to install Super Collider. Super Collider itself is like 3 different processes with their own memory space on your computer. There's this audio server, there's the language interpreter, there's the graphical editor window. And then you need the Haskell interpreter, and then you need the Tidal Cycles library or anything else like that. And then you need an Emacs, or you need a VS Code or an Atom, or you need some way of being able to tell these multiple different processes, each completely living in its own isolated island in user space. And so Sonic Pi was like, can I make an instrument that's all in one? You download this. This is a binary. You run it. It has the audio synthesis server in it, even though it relies on SuperCollider server. But it had a code editor that was specifically written for kids to be able to write code and live code some music. It had in-buffer visualization of the waveforms. It really felt as if it was a step closer in not being a combination of random projects that you pull together and you have them talk over extremely thin wires, but a thing that was designed to be an instrument from start to finish. And so I find his work very inspirational. And I love how he uses it to, I don't know if he still does that, but he's like live coded, gigs in clubs in the past.
Oh, he totally still does that. Yeah.
Okay.
Yeah, can
Brilliant.
confirm.
I need to go to one of those. It's a whole new way of promoting this practice to people who might at first sight look at it and be like, but why? Why not just grab a guitar or a keyboard instead? And it brings together people from musical backgrounds. It brings together people from computational and programming backgrounds. A lot of his kind of design choices and ethos and so on have influenced the way that I look at and design such systems. And there's no way that that our system can't. There's no reason why it can talk to his as well. But we follow a very different computational paradigm. Instead of this like continuous functions of time, Sonic Pi, for example, still very much follows this idea of trigger discrete events in time.
Yeah, his is kind of scheduler based, whereas yours is curves in time.
Yeah, based, and you can think of it almost as a distinction between a keyboard where you press a key and you have like discrete events, like I press this key right now and this will trigger a series of events. And versus modular synthesis, which is all about these, control voltages that are just abstract, waves. They go up and down and they curve in different ways and different patterns, and maybe they loop, maybe they don't. But each one is a continuous entity over time. And there's this notion of persistence. Like my modules don't magically appear and disappear when I'm spawning them. They're always there. The oscillator is always oscillating. The filter is always filtering. And therefore the music just comes about, emerges as a result of how we actually change the behavior of those persistent systems over time.
Yeah. Do you know, I would like very much one day to see a gig with you and Sam
I would absolutely love that as well.
And I'd love to hear, can I hear the difference, not just in the composer, but in the way it's composed?
So what you just expressed is, can I listen to the ergologics of these systems being different? One of them focuses on this continuous, parameter, whatever. The other focuses on events and triggering and scheduling. These are very technical distinctions in some cases. You can still make music that sounds very similar or exactly the same. They can be kind of computationally equivalent, so to speak. But in practice, it ends up sounding very different. And so my hypothesis is that you will be able to hear some difference in shining through the kind of the cracks of abstraction layers that we've both built.
I look forward to putting that hypothesis to the test when I'm in the audience.
Absolutely, I do too. And then we're gonna run some questionnaires on it and publish a paper.
Awesome, sounds good. Dimitri, thank you very much for taking me through this. I look forward to your next gig. And I think I'm going to go and play with it myself.
Thank you very much, Chris, for having me. And please record whatever little snippets of experiments you make with the module and send them over to the Discord server or anything. We love to see how people use it, because it gives us ideas for what else it can do, other than what we we're too close to it and we have our own biases about what it can do. So
sure, will do.
Brilliant. Thank you very much.
Cheers.
It's been a pleasure.
Thank you, Dimitri. That last part of the conversation makes me think of a parallel between music hardware and regular programming. Because Dimitri was saying you can have these two different ways of coding music, and you could do the same thing in either. You could get the same result with either approach, but in practice you won't. The tool that you choose inevitably influences the shape of the final result. And I think there's definitely a parallel there to our programming languages. All these languages that we have, they're all Turing complete. You could write the same system in PHP or Python, Rust or assembly, Haskell, whatever. You could, but you won't. Inevitably, your choice of language influences how you write and therefore what you choose to write. And we think we choose our tools for what they make easy. But maybe we should also start explicitly choosing our tools for how they reshape our projects, and perhaps how they reshape our thinking. I leave you with that thought. While I'm leaving you with that thought, if you've enjoyed this discussion, please take a moment to like it or rate it, maybe share it with a friend or your social network, and make sure you're subscribed, because we'll be back next week with another interesting voice from the world of development. Until then, I've been your host, Chris Jenkins. This has been Developer Voices with Dimitris Kyriakoudis. Thanks for listening.